theory of light. So we can construct some matrix such that we already know that ray can travel along a straight path, and after some operation, maybe reflection and refraction, so it can change its direction. So to determine the point or the locus of the light, we have to take some coordinate. So as it happens within a plane, so we can take two coordinates are sufficient to represent the point of a optical path. So what will be the point? One will be and that can represent the position of a particular point of a ray. So for that case, we can let us consider one ray is going from O to A. So how can I represent the point O? So for that case, we can construct a baseline that is say that is x-axis or x. The height from the x base to O point, say h1, and let us consider the angle between OA ray and the axis x have some value. Let extend this ray, so it has some value alpha. So we can represent the O point as h1, alpha. Similarly, we can represent this point as h2, alpha 2, that is alpha 1, if we consider alpha 1. For that case also, only one ray is going, so its direction is not changed. So we can say that alpha 1 equal to alpha 2. But for representation, we have to we require at least two coordinates. So that's why we can consider one height from a baseline and angle with the baseline. If after A, if some reflector or refractor is there, so it will be like that. So that time we can say that the angle between the baseline and the ray will be changed. That's why we require minimum two coordinates to represent a point on the optical path. Okay. So now we have to know the operation on an optical path. Basically, in ray optics, we can see three types of optical operation. One is translation, another is reflection, and third one is diffraction. So for translation, we have to construct a matrix which can represent the translation operation. So for that case, we consider a ray OA. So for OA, we consider a baseline x. So the height of O is x1 and height of A from x is equal to, consider x2. As only translation is happening there, so we can say that the direction or angle of the line should be equal to constant. Angle of the line with the axis should be equal to constant. So consider alpha. If we consider with respect to O, then it is alpha. If we consider with respect to A, then it will be alpha 2. Basically, alpha 2 and alpha 1 should be same. So now we have to construct the relationship between x and alpha. For that case, we can draw this line, and we know that as it is the same line AOB, as it is the same line, so we can say that if that is alpha 1, that also be alpha 1. So we can say that tan alpha 1 should be equal to this much amount height, x2 minus x1. So x2 minus x1 by distance between 2 points, the parallel distance between 2 points x1 and x2 point. So it will be d. As alpha is very small, or we consider only the paraxial ray, for that case alpha 1 should be equal to x2 minus x1 by d. So if we see the relationship between two coordinates. One is x2 alpha 2 and another is x1 alpha 1. We have to ultimately construct the relationship between this point and this point. For that case, we get two relationships. One is alpha 2 equal to alpha 1, equation number 1, and equation number 2 will be alpha 1 equal to x2 minus x1 by t. Equation 2. So x2 will be alpha 1 into d plus x1, and alpha 2 will be if we write this x1 plus alpha into d, alpha 1 into d, and alpha 2 equal to alpha 1. So here x1 is not there, so 0 plus alpha 1. So from these two equations, equation 3 and equation 4, we can construct a matrix x2 alpha 2 should be equal to 1 alpha 1 d 0 1 into x1 alpha. So that is the matrix representation of the translation operation of an optical path. Now we have to go for another operation, reflection. This is fine, then that will be also fine. And we consider this, that is alpha, and that is alpha 1, and that is alpha 2. So from the triangle AOC, the triangle AOC, we can see that angle alpha should be equal to 5 plus alpha 1, and alpha 2 will be equal to 5 plus alpha. So here we get two equations. One is alpha equal to 5 plus alpha 1, and another alpha equal to alpha 2 minus 5. Alpha 2 minus 5. So if we adding this two equations, alpha will be equal to alpha 1 plus alpha 2. So we can show that alpha 2 equal to 2 alpha minus alpha 1. And what is alpha? Alpha is the angle between the principal axis and the radius of curvature. So if the height of the ray is x1, then we can see that tan alpha equal to x1 by the distance means r. So alpha will be equal to x1 by r. So 2 into x1 by r minus alpha 1 will be alpha 2. And we know that for reflection there is no change of height between the incident ray and the reflected ray. So x2 will be equal to x1. From 1 and equation 2 we can get x2 equal to x1 plus 0 and alpha 2 equal to 2 into x1 by r minus alpha 1. So if we construct the matrix x2 alpha 2 will be equal to 1 0 2 by r minus 1 into x1 alpha 1. So this is the matrix representation of the reflection operation. R is the matrix representation of the reflection operation. Then we have to go for the refraction operation. For refraction, here also we consider one curved surface medium. Basically, it is concave shaped medium. If we consider that light is going from that direction and this is the radius of curvature. Obviously, that is the normal to the curved surface. And if we draw the refracted light, then it will be this one. This one. If we extend this, it will form this line which cuts the principal axis at B point. So the incident angle will be, if it is the point is called N, then the incident angle will be ANO. Incident angle or I will be ANO, and the refracted angle R will be this one, BNO. And consider this angle is alpha 1, this angle is alpha 2, and this angle is alpha. And we know that is the radius of curvature, so ON will be R. So from the triangle NNA, if we consider the triangle ANO, for this triangle, we can see that alpha equal to I plus alpha 1, and from the triangle BNO, we see that alpha equal to R plus alpha 2. So what will be the value of I? I will be alpha minus alpha 1, and R will be alpha minus alpha 2. And from Snell's law, we know that mu1 into sin I equal to mu2 into sin R. If the angle is very small, or we can say that if the ray is paraxial, then we can consider mu1 into I equal to mu2 into R. So mu1 into I means alpha minus alpha 1 equal to mu2 into alpha minus alpha 2. So from that equation, we can calculate alpha 2 equal to, what will be alpha 2? Alpha 2 equal to mu2 minus mu1 by mu2 into alpha plus mu1 alpha 1 by mu2. This one, alpha 2, and we already know that due to refraction there is no change of height, so we can tell that x2 should be equal to x1. So from these two equations we can construct another matrix, x2 equal to x1 plus 0, and alpha 2 equal to mu2 minus mu1. Oh, we have to put alpha 1 at tan alpha 1 value. What will be tan alpha 1? Tan alpha 1 will be, if we calculate tan alpha equal to x1 by r, so alpha 2 will be equal to x1 by r into this one. Then we can construct the matrix x2 alpha 2 will be equal to, and we know that x2 equal to x1, so we write mu2 minus mu1 by mu2 into 1 by r x1 plus mu1 by mu2 into alpha 1. So alpha 1. So the matrix will be 1 0 mu2 minus mu1 by mu2 into 1 by r mu1 by mu2 into x1 alpha 1. So that will be the refraction matrix, representation of the refraction matrix in matrix form. Reflection by the curved surface. So for that case, that is the incident wave, incident ray, and that is the reflected ray, and that is the radius of curvature. So how many operations are there happened in this phenomenon? 3 types of operations are there. One is, at first, this ray AO, ray should go from A to point O. So that means that is one type of translation. And second one is when it falls on point O, then reflection will happen. So reflection, second phenomenon. And third phenomenon, after reflection, then the ray will go along the OB path. So that is one kind of translation. So three type of operations are there. If we consider x2, the final coordinate of the light is x2 alpha 2, then that will be equal to some operation matrix into this initial point x1 alpha 1. So what will be the operation matrix? At first translation. So translation into x1 alpha 1, then after that reflection, then another translation. So if we multiply at first translation matrix with x1 alpha 1 and after that reflection matrix, then after that translation matrix, then we can get the final destination of the light point under some boundary condition. So we can say that if we make it in the reverse way, then what will be the condition? If we make it as a reverse way, then x1 alpha 1 should be equal to TRT inverse of x2 alpha 2. TRT inverse into x2 alpha 2. So if we consider that T is matrix A, R is matrix B, T is matrix C, then it will be A, B, first A, then A, B into C into x1 alpha 1. So here it will be C, B, A inverse of x2 alpha 2. So if we inverse the matrix, that will be inverse of C A B whole inverse should be equal to A inverse into B inverse into C inverse into x2 alpha 2. That indicates if we reverse the operation, then operation order should be similar way. That means at first the translation C will be generated and then reflection B inverse. B inverse means the direction of reflection will be opposite to the initial case. And next one will be translation that represent A, only just reverse, it will happen the reverse way. So that proves the rectilinear propagation of light. So using the matrix method, we can easily prove the rectilinear propagation of light. So that is the end